So this is the last video for this lesson. Okay, so we want to find the transition matrix from B prime to B. And so what we need is that the transition matrix from B prime to B is going to be equal to the matrix whose first column is the coordinates of U1 prime relative to B. The second column is U2 prime relative to B. And then, and that's it. Okay? So we just need to find those two and then plug them in. Okay? And so this will be the first column, and this will be the second column, and then we'll be done. Okay? From that. Okay, so U1 prime, I want to express U1 prime as being a linear combination of U1 and U2. Okay, so this is 1 comma 1 is equal to C1, 1 comma 0 plus C2, 0 comma 1. And so we're just going to find C1 and C2 such that this equation holds. And so hope you see that this is obviously 1 and this is obviously 1, right? So since C1 is 1 and C2 is 1, the coordinates of U1 prime relative to B this is B with U1 and U2 is equal to 1 comma 1. And so the first column is 1, 1. Okay? Now U2 prime is its coordinates relative to I'm going to reuse C1 and C2 here. So it's coordinates of U2 prime relative to the new basis B is now also C1 C2 here. So we just need to solve for C1 and C2 in this, and then those are the coordinates of U2 prime relative to the new basis B. And so this is C1 times 1 comma 0 plus C2 0 1. But U2 prime is 2 comma 1. Okay? And so C2 here is 2 and C2 here is 1. And so the coordinates are 2 comma 1. Okay? And so the coordinates of U2 prime relative to B is 2 comma 1. And that's the second column. Okay, so the transition matrix from B prime to B is this matrix there. Okay, that's the transition matrix. So in example 1, we find the transition matrix from the old basis B prime to the new basis B using this method. Okay. Okay, and so part B is finding the transition matrix from B to B prime. And let's keep moving. So in example 2, you're going to let B and B prime be bases in example 1, in the last example. And so I'm going to find the coordinate vector of V relative to B, given that the coordinate vector of V relative to B prime is equal to -3, 5. Okay, so we have the equation that the coordinate vector of V relative to B is equal to the transition matrix from B prime to B times the coordinate vector of V relative to B prime. Okay, and so we found earlier that the transition matrix from B prime to B is this matrix 1, 1, 2, 1. Right? That's the transition matrix from B prime to B. And so you just plug that in here. that matrix times this, which is negative 3, 5. And you multiply, matrix multiplication, and you get negative 3 plus 10 is 7. And so this is a 2 by 1 matrix. So this is 7 here, and you get 2 there. So the coordinates of V relative to B is 7, 2 as a column vector. Okay? And so in example 2, we find the coordinates of V relative to the basis B, given it coordinates of V relative to the old basis B prime and the transition matrix from B prime to B. So given this and this, we find that. Okay, using this equation. This here, this there, you plug it in, multiply, you get that. Okay. Okay, so if B and B prime are bases for a finite dimensional V, then the transition matrix from B prime to B times the transition matrix from B to B prime is equal to the transition matrix from B prime to B prime, which is the identity. So this is 13, and this is in fact 13 in this section, okay? So if B and B prime are bases for the same finite dimensional vector space V, then if you multiply this times this, you're going to get the transition matrix from B prime to itself, which is the identity. Okay? Okay, and so that leads us to this theorem. Theorem 4.6.1. If P is a transition matrix from a basis B prime to a basis B for finite dimensional V, then P is invertible and P inverse is a transition matrix from B to B prime. So P is a transition matrix from B prime to B for finite dimensional V, then P is invertible and P inverse is a transition matrix from B to B prime. Okay? So that's coming from this equation. It's saying this times this is equal to the identity. These two are matrices. And so if you're multiplying this by this and getting I by the definition of the inverse, these two matrices are inverses of each other. And that's what this theorem is saying. Okay? So for instance, if this transition matrix was for a finite dimensional V, and first off, if you have this transition matrix, it's invertible. And its inverse would be this one. Okay? You're getting that from this times this equals that, you get this theorem. Okay? Okay? And okay? And so a procedure for computing the transition matrix from B to B prime. And so it's this. Step 1 is form the matrix B prime on the left and B on the right. So you have a partition matrix, the left side is B prime and the right side is B. Step 2, right, so so the column vectors of B prime. So you're taking the basis B, which consists of vectors, and you're making them the columns here. And B, you're taking the basis B prime and its vectors, and you're making them the column vectors on the left side here. Okay? So step 2 is you use elementary row operations. To reduce the matrix in 1 to reduce row echelon form. So you want to take that matrix and get it to reduce row echelon form. And then step 3 is the resulting matrix is the left side is the identity and the right side is the transition matrix from B to B prime. Okay, step 4 I could write, it would just be taking this out. So that's your matrix there. That's the transition matrix from B to B prime. That's what we want to find. Okay? So step 1, you form this matrix, right? And the column vectors, vectors are the basis vectors in B prime of B, right? So the column vectors on the left side are the basis vectors in basis B prime. And the column vectors on the right side are the basis vectors in B, basis B. And so you have that matrix, and then you use elementary row operations to transform this matrix to reduce row echelon form. And when you do that in step 3, the left side will be I, and the right side is the transition matrix from B to B prime that you want to find. Okay? So the old basis goes on the right side, and the new basis goes on the left side. So new basis on the left side, old basis on the right side. Okay? You take the basis vectors in your basis and you make them the column vectors on either side of the partition. Okay, and so that's the 3-step procedure for computing the transition matrix from an old basis to a new basis. Okay, and so example 3. So for example 3, we're going to consider the basis B, which is U1, U2, and the basis B prime, which is U1 prime, comma U2 prime, for R2. So these are 2 bases for R2, and such that the same, we're going to go U1 is 1, comma 0, U2 is 0, comma 1, U1 prime is 1, comma 1, and U2 prime is 2, comma 1 again, okay? And so we're going to now use this new method to find the transition matrix from B prime to B, okay? And so we're going to take the new basis on the left side and the old basis on the right side. And that's the same as having the new basis B on the left side and the old basis B prime on the right side. The B and B prime, it's not where the prime is that matters. It's what you're considering your old basis and your new basis. Okay, that's what's determining where B and B prime goes. What is the old basis and what's the new basis? The left side of the arrow is your old basis. The right side of your arrow is your new basis. Okay, in the notation. Okay, and so this is a procedure to find the transition matrix from the old basis B prime to new basis B. And so you have this partition, and the goal will be, so now this is equal to, these are the basis vectors for your new basis B. This will be 1, 0, 0, 1. And then U1 prime is the basis vectors for your old basis. That's 1, 1, and 2, 1. Okay? And so this is a very simple example, because if you get this to reduce row echelon form, you actually end up with the exact same matrix. So this is already in reduced row echelon form. Okay? There's a leading 1 each non-zero row. The 0 rows are grouped at the bottom. The leading 1 in the lower rows rows to the right to one above it, and every column with a leading 1 has 0 everywhere else, right? So this is a matrix in reduced row echelon form. It's the same thing. And so now we know the left side is I and the right side, this is equal to, now the left side is I and the right side is the transition matrix from B prime to B. Okay? And so this is the transition matrix right there. The transition matrix from B prime to B. is equal to that matrix 1, 2, 1, 1. Okay, and so we found it. And so if this was just a more complicated example, you would just have to do some work to get the matrix you started with to reduce echelon form. But that would just be boiling down to doing an earlier problem where you get a matrix to reduce echelon form, right? And so this method is pretty easy. And so you would start with the new basis on the left side, the old basis on the right side. You get to reduce echelon form. The left side is I, the right side is the transition matrix. Okay, so this is probably a good method to use when you find the transition matrix from an old basis to a new basis. Okay, and so that's example 3. And example 3 is a good example to study when learning or studying how to find a transition matrix for computing it. Okay, and now theorem 4.6.2 is let B prime equal to the set U1, U2, Un be any basis for the vector space Rn, and let S equal to the set E1, E2 to E sub n be the standard basis for Rn. If the vectors are in column form, then the transition matrix from B prime to S is equal to this. This is equation 15 in this section. This is theorem 4.6.2. Okay? So I'm going to let B prime be any basis for Rn, and S is the standard basis for Rn. And so these vectors are in column form. This is in column form, that's in column form. They're all in column form, and the ones in the middle. Then the transition matrix from B prime to S is just the vectors of B prime as the columns of that transition matrix. Okay? And so that's if you have a basis B prime and you have S as the standard basis for Rn. Okay? Then the transition matrix from B prime to the standard basis is that. Okay, and that's that theorem. Okay? And if A is equal to something like this. Okay, so if A is that matrix, and it's an invertible n by n. So it's if that's an invertible n by n matrix, then you can say that A is also a transition matrix from the basis U1, U2 to Un for Rn to the standard basis for Rn. Okay? So if A is this matrix, and it's invertible in n by n, then A is also a transition matrix from this basis for Rn to the standard basis for Rn. Okay? And that's from here, because this matrix is equal to transition matrix from basis for Rn to the standard basis. Okay? And so just given an invertible matrix, an n by n invertible matrix, it can act as a transition matrix. Okay? And so that's the end of 4.6. And so I'm going to stop this lesson here. And so the next lesson we will finish chapter 4. Okay.